Okay, so just to repeat, the band diagram is it's a potential diagram. So if I take a block of any material here, mostly we do semiconductors, obviously. So this is the X direction, that's what it's showing. And this is the increasing potential of an electron. That's what the band diagrams are. And typically there are few notations in band diagrams. The first is two lines, which shows, so I'll show, it's called EC, sorry. This is EV, and then you have another band called EC. And this is what's called the valence band. And this is called the conduction band. Okay. Now, typically in a material, especially in a semiconductor material, these are the two bands or accepted energy available for electron in that material. And this gap is what's called, if it's the forbidden energy or the band gap. Forbidden energy or the band gap. Okay, for example, in electron is 1.1 electron. So if an electron needs, if this material needs to conduct, then a electron needs to be in the conduction band. Okay, so your electron has to have enough energy to reside in the conduction band for it to conduct. I think people are joining without muting. 1 second. Okay, so your electron needs to be in this conduction, above the conduction band for it to conduct. It needs to be above this. If you have holes or positive charges, okay, actually I shouldn't draw the circle, they mean immobile charges. So if you have holes, then they need to be below this valence band for it to do conduction, and nothing is allowed in between this. So these are the two bands which we talk about. Sorry, just give me a second. Okay, sorry. Okay, so those are the two bands which we talk about in band diagrams. The other band we talk about is what's called the Fermi level. Okay, so we talk about Fermi level, and Fermi level is nothing but it basically tells you what is the probability of an electron to occupy a state, and a state is nothing but so these levels are called states. Okay, a state 50%. So what's the 50% probability of an electron occupying the state? Now in reality, electron or hole cannot occupy any of this forbidden stuff, but a Fermi level can be anywhere in between because it's a probability. It's just telling you on average what is the level of energy. So for example, in an intrinsic semiconductor, which we'll talk a little bit later, the Fermi level can be here. You know, this Fermi level stuff will come when we are deriving the threshold voltage for the MOS. So that's why we are talking about it. Okay. And the other energy band we talk about in band diagrams is the free space, which is like, you know, a point where there are no charges at all. So that's, we call it the E0 or the free space energy. Okay, so for example, if you have to take a electron from the conduction band to the free space, that's what's called the affinity of an electron. And if you want to take an electron from the Fermi level, the energy, that's called the work function. So if you see the term work function, that's usually what it means. It's like, what's the energy required for us to take an electron from this Fermi level all the way to free space. Free space means it's a point in space where there are no charges, nothing at all. Okay, so that's kind of a quick overview of band diagrams. So now I'll show you different types of band diagrams for different types of materials. I think again, you guys are aware of this, but we'll just repeat it for sake of completion. One second. All right. So typically in VLSI or semiconductor, we usually talk about three types of materials. Okay. So the metal, obviously, insulators, and semiconductors. Now, if you look at the band diagram of metal, its conduction band and Fermi level, they're actually the same in the sense that all the electrons are actually above the conduction band, so which means that plenty of electrons, I apply electric field, and I have conduction, right? And examples of metal obviously are, you know, copper, aluminum, and so on, gold, and so on. And you can see here, there's a work function which tells you that if I want to take electron from the Fermi level, which is actually the conduction band as well, to free space, it's about 4.1 electron volt. Okay. For insulators, the separation between valence band and the conduction band, you can see, is very large compared to most materials, which means that most of the electrons are in the valence band. The chances of me having this electron go into the conduction band is almost zero. So which means that there is no conduction at all. So no conduction for insulator. So it's, as the name suggests, it insulates from whatever two plates or two conductors you might have. And the affinity of the electron, if you had one here, it's about 0.9 electron volts if you had electron in the conduction band. Obviously, the examples of insulators are silicon dioxide, air, obviously, and wood and so on. So these are all insulators, plastic and so on. Okay, so that's the insulator. Now, semiconductor is somewhere in between, in the sense that the valence band, that means the electrons in the valence band are separated from the conduction band by a certain amount of energy, which is called the band gap, because this is the gap in the conduction band and the electron volt. But this band, you can see, is much less than, for example, in the insulator. Obviously, there is still a gap, unlike the metal. In the metal, it's just the same. So that means all the electrons are in the conduction band, free electrons. Here they are not. In a insulator, in a semiconductor, most of the electrons are here. But what happens is at room temperature, some of them escape. And I'll show you some lattice diagrams. It will be much more clearer there. They will escape here, but when they escape, they actually leave a hole, which is a positive charge behind. So every electron appears here, there is a positive charge here at room temperature because of this thermal agitation. But they are very few in number. They're still not enough to do conduction, a very small amount of conduction, okay? So those are what's called the intrinsic semiconductor. And in intrinsic semiconductor, the Fermi level, this is the Fermi level, is pretty much halfway between the conduction and the valence band. That's because every time an electron goes, it actually leaves a hole behind. So if you take the average energy, it's almost halfway in between. Who is annotating this? Can you please stop annotating? Okay, thank you. I need to increase. Okay, so that's what's called the Fermi level of the semiconductor. Now you can dope it. We'll show exactly what doping means to make it a more p-type or a n-type. So that means have more positive charges or negative charges compared to the electron intrinsic level. In that case, what you have is you get a um, um, Fermi level, which is either lower if it is number of holes or higher, and or higher than the Fermi potential. And this quantity is called the Fermi potential. This is called the Fermi potential, which is a function of your doping. And I'll explain doping a little bit. I'm just going a little bit ahead, but I'll explain that. Okay. So this is just showing, so I explained quickly what band diagrams are, and then we just explained the types of materials in terms of their band diagrams. Now I'll go and show you what the different types of semiconductors, how to create extrinsic semiconductor, what's the difference between intrinsic and extrinsic semiconductor, and how to create them, and show the band diagrams for them as well. Okay, so any questions? So what we'll do is I'll try to go through maybe the slides first, and then in the end we can take questions. I can come back and take questions, but in between, wherever you don't understand, just there is a raise hand. I think you should all see a little icon showing raise hand. You can always raise the hand and ask the question. Okay. All right. So I see two participants raise the hand. Okay, go ahead. What's the question? Dinesh and someone else. What's the question, Dinesh? You need to unmute yourself first if you haven't. Okay, did you have a question or you're just trying out?
So what is Fermi potential?
So like as I said, Fermi potential, I just explained, it's the probability of an electron holding a certain state, and the probability should be 50%. So what it means is, so it just basically shows you what is the doping. So if you forget the definition and all that, the Fermi potential actually shows you what is the type of the material, and we'll cover as we go along. I'll show you more. So if your Fermi potential is right in the middle, which is equal to this intrinsic level, that means you don't have excess carrier. If it is lower than this, that means you have a lot of positive carriers, holes. If you have higher than this, that means that material has a lot of negative charge carriers for conduction. Okay, so that's what Fermi level means. So for example, if you have electron, if you dope it with something where there are a lot of electron, where the Fermi level is now very close to conduction band, now you need a very little energy to move to the conduction band, which means that the number of electrons available for conduction goes up at room temperature compared to an intrinsic level. So for example, in a semiconductor, the entire band gap is roughly 1 electron volt, which means that this is half electron volt, which is actually a lot as a Fermi level. But let's say you dope it such that now it's only 0.1 electron volt. Now, even at room temperature, you have enough electrons which can jump into the conduction band and be available for conduction. Or if you dope it the other type, where it is p-type, then you'll have enough holes here. So if your Fermi level is very close to the valence band for a p-type material, then you'll have a lot of holes for it to conduct as well. So either you can have negative carriers or positive carriers. Either one of them will be conduction. Okay. All right.
Yes,
So
yes.
okay. So I think once I'm kind of going a little bit ahead as well. So I think if I go through next few slides, it'll be much more clear. So this is again showing, so silicon is obviously the material we probably use in 99% of the ICs we design today. So that's like the most preferred base material for making chips, right? Silicon. And if you take the lattice structure of the silicon, then it has 4 valence electrons, which means that when it bonds, it perfectly bonds on the side 4 electrons to form a perfect lattice. What it means is that then it just bonds so nicely that it creates this crystal structure without any free electron available. But what happens is at room temperature, some of them break. Okay, some of them will break, and they will create. So, for example, let's say there is enough thermal energy. This bond might break and release this electron. Okay, but obviously, once you release this electron, there is a vacancy here, and that vacancy can be filled by another electron from here, right, to create that bond. So you have 2 sort of mobile charges here. So you have 1 electron, obviously, you put an electric field. So you have 1 electron here, you put some electric field here, right, applying a voltage, then this electron will move in this direction, actually in the opposite direction. Or an electron can move and fill this gap and create a gap here. Another electron can move here, fill this gap, and this will create a gap here, positive, and so on. So in other words, what it will look like as if a positive ion is moving in this direction if I apply the same electric field. So electron moves this way, positive moves this way. Now, because in an intrinsic semiconductor, they're exactly the same, a lot of them recombine. So you don't get a lot of conduction current. Okay. So that's an intrinsic semiconductor. And if you look at the um, the band diagram, which I just showed before, the same thing. You have a valence band, you have a conduction band, and you have a forbidden gap of 1.1 electron volt. Most of the carriers are here, but at room temperature, they're actually lattices. At room temperature, some of them can break into it, but they are very small. I think they're about like 1 in 10 to the power 10 atoms of electron carrier, which is a lot less to do any meaningful conduction. So it's pretty much a insulator. So that's what's called, so this is what's called the intrinsic semiconductor. Okay, so intrinsic semiconductor in the sense it's just pure silicon or a pure germanium. There is no impurities added in that. Now, this is good, but if you want to create a conductor, if you want carriers, what people do is what they do is what's called doping, and those are what's called extrinsic semiconductor. So the way you dope them is, for example, if you want to make an N-type. So if you want to make N-type, that means you want to have a lot of electrons for conductions. Or in other words, you want to have majority carriers, electrons as your majority carriers. If you want to do that, you go to the periodic table and choose the elements which has at least 5 electrons in their valence band. So for example, all these elements here, and some of the popular ones are arsenic and antimony. For example, in this example, you have doped it with antimony. When you dope it with antimony, obviously one antimony will get lodged into this crystal structure. It'll find 4 electrons to bond with these 4 uh, silicon atoms to bond with, but it has an extra electron which is kind of free to move, right? So that electron has enough energy to actually conduct now in the current. And obviously, if it goes away, then it will leave actually a positive charge. But this is a positive charge which is immobile in the sense that, unlike in the silicon where you are forming a bond, the bonds are formed. So if you look at the charge, it's just a positive charge, but it cannot move in the sense that another electron cannot come here and take its place because it's a free electron. It's, in your previous case, in this case, you are breaking a bond. You're breaking a bond and going here. So another electron would come and form the bond and leaving another bond here and so on. So it looked like a positive charge. In this case, the positive charge is actually, it looked like a mobile positive charge. In this case, it's immobile in the sense once the electron moves away, it looks like it as if it left a positive charge here, but you cannot move it. In other words, you can generate electric field out of it, but if you apply electric field, this will not conduct. Okay. And when we do PN junction, hopefully that will be more clear. Now, if you look at the band diagram, previously you had this as your Fermi level, that's your intrinsic level. That's your, now you have enough carrier, negative carrier, that the Fermi level is much closer to your conduction band, like I said. Now the probability of these energy levels jumping into the conduction band is much higher now, which means that I have a lot more free electrons at room temperature than I had before. So that gives you the ability to conduct. And if you look at the block of the material, you can see a lot of these electrons here, mobile electrons, right? And you also have these positive charges, which are holes. That's because even in this, some of the semiconductor might break like before, because they have enough thermal energy to break and create electron, but that leaves a hole behind. So those are what's called regeneration. So a hole and electron pair is created. But for the antimony, for the doping ones, every time an electron is there, there is an immobile positive. So any circle you see, that one cannot move. This one can move. So this positive charge I have, I apply electric field, this will move. But if I apply electric field here, it'll just go and, if the electric field is in this direction, it'll just stop there because it's a positive charge. It'll not move it, or it'll create a dipole. So that's what's called a extrinsic semiconductor. So basically, just in simple terms, you want to make it more conductive silicon, you dope it with some 5 element, which has 5 valence electrons. So when you dope it, there are enough arsenic or antimony atoms which gets lost per cubic meter of volume inside the silicon, such that it gives you free electrons per electron volume, enough for you to conduct. If you want it to be heavily conductive, you dope it really high. When I mean by dope it really high, what I mean by that is the concentration of the dopant. So here, for example, you'll hear the word dopant. So arsenic or antimony is called the dopant, right? Because you're doping it, you're basically doping the intrinsic semiconductor, intrinsic silicon, to make it conductive. Okay, and so you'll see in VLSI a lot of times it's called a N-well, sometimes it'll be called N plus, sometimes it'll be called N plus plus, and these are to do with the level of impurity, okay. So for example, when they say N-type, they typically mean your doping is typically less than 10 to the power 15 atoms per centimeter cube. So which means that these many electrons are available for you to conduct in a centimeter cube of volume, or these many antimony or arsenic atoms are there per this thing. And you'll see a lot of times, like for example, when you do the MOS, you'll see the source and drain are called N plus. Now N plus means it's heavily doped. Okay, it's called heavily doped. And that typically means that your doping is greater than 10 to the power 18, I believe, per centimeter cube. Okay, roughly, these are guidelines. Sometimes they can be less too. So when people are saying N plus, that means you have a lot more electrons per cubic centimeter available for conductions. When they're saying N type, or sometimes they'll call N minus, then it's even less, much less than this. It could be like 10 to the power 6 or 10 to the power 15. Okay. So that's how you create a N-type material. Any question? Like I said, if you have some questions, we can come back, but there's some doubt you absolutely have to clear, you can raise your hand. Yeah, hi, Chandan, go ahead. What's the question?
So here the electrons which are created due to doping,
Yeah,
the free electrons, and the electrons which are due to the breaking of bond of
yeah,
silicon,
yeah.
they must have difference in their energy levels.
Yes. So the ones which are, so if you go back to this diagram, I think that explains it better here. Well, I can just draw it here. So the so just to repeat the question for everyone. So what Chandan is asking is that this electron which broke in, let me do it in red here. Red here. So let's say this bond broke here. So you created an electron and a hole pair, right? Now the thing is that this electron might have energy very close to this. So the Fermi level energy might be very close to this. But the thing is that it also created a hole which has a Fermi level right here too. So you created a hole and you got created an electron. So that's why the average electron turns out to be here. Okay. Whereas in case of the arsenic or antimony, when it breaks, you have an average electron level here, but there is no holes created. So which means that you have all the electrons for conduction right now. Because once you create this hole here, the chances of these two recombining or some another electron coming and recombining and creating back this lattice is higher. So which means that you may not have it for conduction. You see what I'm saying? Did that make sense?
Yes, sir. Yes, sir.
So that's why when you have a lot of generation and recombination, in effect, you don't get that much unless you put electric field and separate them. But at very high temperature, that's what happens. Actually, a lot of these electrons break and you actually have it for conduction as well, because these will go to the negative terminal, these will go to the positive terminal, and you'll get a conduction as well. So you can get. So the energy level of the electron just tells you if it is moving into the electron band. But what is more important is the average energy of all the electrons, like the probability. Like if I just want to see at the probability, like how much electron I'll get for conduction, that's reflected by these Fermi level. Okay. All right. So if you don't have any other question, I'll move to the next one. So next one is basically just sort of the opposite of what we described in the p-type. So I'll go a little quicker here. So now we want to create more holes instead of more electrons. So you do the opposite. Instead of going with one extra electron, you go with uh, elements which has one less. So you go with the 3-type. So one popular one which goes well with silicon is boron. So if you take a little bit of boron, and again, the same concept here. So here boron is called the dopant. And when you're saying P, that means you have about, less than 10 to the power 15 atoms per centimeter cube of boron, or if people are saying it's P plus, then it is, greater than 10 to the power 18 atoms of boron per centimeter cube. And it's the same concept. And for the p-type, it's the opposite in the sense, so because you have few borons for, a large amount of the crystal lattice in silicon. So for example, here boron comes in, it finds, 1 bond, 2 bond, 3 bond, but that's it. It has only 3 electrons, so it's done. So which means that this silicon over here doesn't have another electron to bond with. So this electron is free now for this guy. Okay. So which means that it creates a hole because now some other electron can come in and fill in here, or for example, fill in here. So that looks like as if a positive charge is moving in. And if you look at the band diagram, because it is positive, the energy moves in the opposite direction. So if you have a lot of positive charges, then the Fermi level will actually move in this direction, because if you have positive charges here, then you can conduct here. If you have negative charges in the conduction band, you can conduct here. So the Fermi level of the p-type is closer to the valence band. And if you look at the material, same thing like before, you get some holes and electrons because of these bonds breaking, just like intrinsic semiconductor. But because of the boron, you get a hole, but because that hole can move away, you actually get an immobile negative charge. So this is immobile now. So you can't put an electric field and make it conduct. It's immobile, just like in the n-type. Okay, so that's, like I said, everything I explained in the n-type appears here is just kind of the complementary case for it. Again, any dying questions before I move? Like I said, we'll come back and quickly review it if you have any questions, or we'll just ask questions in the end. Okay, so now we'll create a junction from these two materials, and I'll quickly explain it just from a point of band diagram, and then I'll show you just the effect of the PN junction. Will not derive much of it, and then just explain qualitatively the MOS transistor. Okay, so now if you bring in two materials, so let's say we do a P plus and bring and join a N type material here. So if you, again, can you please mute anyone who doesn't have it on mute? I don't know, somebody is not muted. Can hear some background noise. Okay, good. So now if I look at it from a band diagram perspective, so I have for this N-type material, I have this conduction band here. So let's call this EC, and I have this P-type material here for this thing, and I have, sorry, this is the valence band for the N-type. So let me just draw a little dotted line here, and then I have the conduction band for this guy, and the Fermi level for the P plus is somewhere here. The Fermi level for the N type is somewhere here. Now thermodynamics tells us that that cannot happen. If you take a material and join it, the Fermi level should be the same everywhere. Okay. Now the problem is I can't just say the Fermi level will be this now, because then that means this is become intrinsic now. This is also become intrinsic, but that's not true. This is a P type. This is an N type. So I still need it to be N type, P type. And on top of that, you have a huge potential difference here. And you know the electric field is potential difference divided by the distance. If you have a potential difference with a distance of 0, that means this electric field will be infinite if this is 0, and that's not possible either, right? So then what happens is that's when you get what's called the band bending. So I'll just draw the diagram, and then so and let me draw the conduction band here. Actually, I drew the opposite, but that's okay. I'll just flip the, and let's say now this is the resultant Fermi level, which has to be constant. According to thermodynamics, this has to be constant. So I kind of switch the PN type. So now this is my PN junction. And let's call this, sorry, this is not very symmetric, but just bear with me. So I kind of drew it opposite. So this is P plus N. So now if you look at this side, far from this junction, we'll talk about the junction. It is still a P type, like it suggests here, P plus type. And if you look far from this junction, this is N type because it shows the Fermi level is close to the conduction band. And in between, you have this potential drop. Okay. And this potential drop happens because you can intuitively see, because you have a lot of free electrons here. What that'll happen is, because you have a potential difference, they will move to this direction and leave an immobile charge. And because they do that, you get an electric field, because if you have immobile electric charges and you have these negative charges also, they will create an electric field. And this will keep happening till this is balanced. This potential difference is balanced. So whatever potential difference this is, Q times phi, this electric field will keep doing that till this is balanced. And once it is balanced, then it will stop. So this is what's called your depletion region. It's called depletion because it is depleted of carriers, either negative carriers or positive carriers, okay? And this is called a built-in potential, which is typically about 0.6 to 0.7 volts. Okay, and if I have a diagram, I think, so this is just showing, so if you take the P plus and N junction, you can see after they have settled, that is what's called equilibrium. This is the concentration of your acceptor ion. So for example, this is boron, this is, let's say, antimony. That's the concentration it's showing. Now, typically they are never this abrupt. You have to have some gradation because it creates physical problems. And because of this depletion, you get some negative charges here, negative charge. This is the total amount of negative charge, which has to be obviously equal to the positive charges here. And that obviously creates this gradient electric field, which is exactly, if you integrate that, that should be the potential difference between the two bands. Okay. Like as I said, understanding band diagrams requires a lot of device physics. The only reason we are talking about this is if you kind of understand why the band is bending, just to kind of equate potentials and so on, or like for example in depletion. So for example, mark this, that when you have an N type or you have a P type and you have a depletion, the band has to bend for it to become a P type. Like for example, previously in the P plus type, you can see wherever you have this thing, it will bend. And this will help you in visualizing why we get a channel in MOS transistor. When I explain the MOS transistors a little bit later, it'll actually help you sort of visualize it better. So you can see that anytime you have charge or potential differences, your band is going to bend because that's the potential difference it's showing you, because it's a band which is showing you the potential energy of your electron. So when you're bending, it's basically showing you the potential difference between those 2 points. For example, this bending here is showing the potential difference between these 2 points. So there is a potential difference which is about like I said, 0.6 volts or 0.7 volts. Okay. Oh, another thing I wanted to mention is, so if you have electron and jumps to the conduction band, it needs at least in silicon, for example, this 1.1 electron volt. Now let's say you have more energy. So for example, let's say you get 1.2 electron. So it'll use the 1.1 electron volt to jump, and the rest of the energy is actually converted into kinetic energy. So basically that's what does all the heat and your Brownian motion and all that stuff. This is even if before you apply any voltage to it. Okay, any quick questions? Like I said, we'll just quickly review it after. Any quick questions? Yeah, go ahead, Chandan. What's the question? Yeah, looks like Satabdi also has a question. Go ahead, unmute yourself and ask the question.
So my question was when the level of number of donors and number of acceptors will be same, then it will behave intrinsically. So how can we compensate that problem?
You mean if you dope a certain silicon with same amount, you mean?
Yes, sir. I am doping P and also N.
But why would you do that? You're just asking, are you curious, or you're saying, no, I will do that?
No, I am just curious.
Okay, so well, the thing is that first of all, if you do that, you'll be worse off than intrinsic. So for example, if you dope with the same amount, then they will just recombine, right? And whatever is available for conduction, they are conducting now in what's called in an extrinsic semiconductor. So if you have electrons, if you have free electrons in an intrinsic semiconductor, what's called the mobility, which gives you the current carrying capacity, it is far better than in extrinsic semiconductor. So if you want a free carrier, you want it in intrinsic. If you want extrinsic, then you either want to make it positive or negative. If you make them equal, then it is no better than the intrinsic one. On top of that, your mobility is also lower than that. Did that explain?
Sir,
Yeah.
sir, here we can see that the depletion region is more wider towards the less doped region.
Yep.
Sir, could you please explain why?
Okay. So the question is, by the way, Satabdi, did I answer your question or it?
Yes, sir.
Okay. All right. So the question is, why is it more here than here? So as you can see, I've written P plus here. Now the question is, why did it do a P plus? That again, it's a little involved because you can't just do N plus. If you do it, your diode, diode characteristics won't be a good diode. Basically, it won't be exponential in nature. Okay, and that's when you derive the equation, and you'll figure it out. So the idea is, one side you make it heavily doped, such that you have an excess carrier, and the other part is just creating electric field which just collects, like in a BJT. Like for example, your emitter is heavily doped, your collector is not, because if you do both sides heavily doped, you create what's called a Schottky barrier, and you have tunneling currents and so on. So this is, it's a little beyond this lecture, but typically when you do diodes, that's how you'll do it, because you want one side you want a heavily positive carriers, the other side you just want it to be electrically swept. Okay, so okay, now the question is, why is it more? Now so if I draw this, okay, so because this is P plus, that means what did we say? This is more than 10 to the power 18 atoms per centimeter cube, right? So this is just a cross section. So if you look at the 3D, kind of looks like that. So per unit volume, there are a lot more carrier than the N here, because this is probably less than 10 to the power 15 per centimeter cube. Now these are obviously balanced, because whatever electron goes from here gets lodged into the other place, right? From the N to this time. So from N, whatever electron goes here leaves the same positive charge. But the number of carriers which it lodges with is a lot more for the same volume here than in this, right? Just because your dopants are a lot thinner here, so it will take more unit volume for the same charge. There are more charges here. So let's say, for example, this was 10 to the power minus 15 coulomb. To get that same minus 10 to the power minus 15 coulomb, I would need 1/16. Here I would need 1 cubic volume. Here I would need less than that. Okay. I mean, when I said coulomb, actually electron coulomb. Did that answer your question,
Yes, yes,
Chandan? Okay.
yes, sir.
All right. Okay, so we'll just quickly move on. Okay, so now this is just without any bias. If you just take a P type and N type, connect them together, this is what happens. Now, what happens if I put a bias? So what I mean by bias is you take a voltage source, and this one we're saying forward bias. So in a forward bias, this side is more positive than the N side. So if you've all seen a diode symbol, so basically this is what we are doing, right? So we're putting a more positive voltage than here. So once you put more positive voltage, again, I will not go into the workings of it. You can follow any of the textbooks if you're interested. But essentially what happens is, when you do that potential, if you calculate the electron density at these edges, they have exponential nature to it. They create a lot of electrons at this point after a certain voltage. And these electrons, once they come into the electric field, they get swept across to it. And because this is the majority carrier here, they get conducted to the other side, and you get electron flow here. Same thing happens here, but for holes. So for holes, you'll get a huge carrier here, and by diffusion and both as drift, it actually has both the action, diffusion and drift. So just to explain what diffusion and drift is, if you have a free electron and you apply electric field, like some material, you have electric field, so you apply a positive potential, negative potential, you get electric field. You get a force Q times E, and this electron moves to the other direction. Obviously it's got this Brownian motion and moves to the other direction, other side of the potential. Actually for electron it will be moving in this direction. That's called drift. Okay. And the diffusion is in a semiconductor. If I just bombard a bunch of electrons, if I want to show like a spike of electrons into this material, and let's say I have some potential across it, then this will actually diffuse just from recombination. Okay, so that's called the diffusion current. So because of these two mechanisms, you get electron flow in this direction and the whole flow in this direction, and that gives you the current, which follows sort of this equation here, which all of you are familiar with. So some IS time approximately is actually 1 minus e to the power the voltage across the diode times VT after a certain voltage. Okay, when you have the voltage is really small, it doesn't give you much of a current. So that's what's called the forward bias. So that's the forward bias current. But in VLSI, actually the forward bias, especially when you're doing CMOS design, you pretty much never hardly ever deal, especially with digital CMOS design, you hardly ever deal with forward bias diodes. You actually most of the time deal with reverse bias diodes. And the reverse bias diodes is obviously the reverse of what we did. We took the same PN junction, but instead of applying positive voltage here, we actually applied a negative voltage with respect to the N-type. And that what it does, it just enforces this electric field. So as you keep increasing this VR, this negative charges here, so more electrons flow from the N-type to here because because of the potential difference we are creating now, and they do that. So essentially no current is flowing, charge is just building up. Okay, and what does it look like if that's happening? So it looks like a capacitor, right? In a capacitor, when you change the voltage slowly, you just accumulate charge, whatever charge you accumulate here, positive charges, you accumulate the charge on the other side, and this charge is equal to what? C times V, and the C is whatever is your material. Let's say you have oxide, that will be Cox will be some microfarad per micrometer square times the area, obviously, times a V. So that's the amount of charge which will be building up depending on the potential. And so the same thing appears here, as I keep increasing the voltage, this just keeps increasing, more charge starts building. But the difference between this case and a capacitor here is, you can see this distance here, so the Cox is some Kox times epsilon naught over D. So that's what Cox is. This D is constant. This D is not varying. But here you can see the effective D. This is kind of your D of your capacitor. That's actually varying with this voltage. Okay, they're kind of proportional. So as V is increasing, VR is increasing, D is increasing. If D is increasing, then your Cox will be dropping, right? So you're effective. So it's what's called a nonlinear capacitor because it's a voltage dependent capacitor. So C is not fixed. It's actually dependent on the voltage. So then this is a nonlinear capacitor. Okay, so I'll show you the equations directly. So that's typically what your nonlinear capacitor looks like for a reverse bias diode. And so this is at your unit capacitance, which is the capacitance per unit square or unit area at VR is equal to 0. Because if you substitute VR equals to 0, you should get Cj equals to Cj naught. And then you can see as you are increasing VR, Cj is dropping, which is divided by this phi naught value, which is a built-in potential related to your doping and so on. Okay. Now, and like as I said, because this is voltage dependent, this is a nonlinear capacitor. And this is very important because all your drains and sources of your MOS transistor, they're actually all reverse bias diodes. So all your signals which are swinging on that node is actually has this capacitance as well. And this capacitance is becoming a dominant one for lower technology, lower fine line technology now, like 7 nanometer and so, because your gate area is so small compared to your drain area, it is becoming significant. For longer channel lengths, like when you are dealing with 0.25 micron or 0.35 or 0.18, this is a smaller portion, but now it's becoming dominant. So since it's voltage dependent, so for example, I take this and vary this voltage from some V1 to V2. Since the capacitor is going to vary, when you're doing, so obviously the simulator simulates this exactly using this equation. But when you're doing hand calculations, it is easier for you to have some thumb rules, like how should I, so for example, if I want to find out the delay of a circuit, instead of doing this entire nonlinear calculation, what people usually do is, sorry, kind of overrode this here. They take the average. And so let's say you're swinging from 0 to, or let's say 1.8 volts to 1 volt. This is your swinging. You can use this approximation here to give you a kind of an average value, CJ average. And then you just multiply that by the area of the diode, and that should give you the approximate junction capacitance. Okay, so this is all I want to cover about PN junctions and band diagram. The next I'm going to just quickly, like maybe 5 to 10 minutes, I'll just show you how a MOS channel forms. And then from next class onwards, I'll start going deeper into the MOS and show you how the transfer characteristics of MOS comes to picture. Any questions, like quick questions, this thing? Yes, Subham, go ahead. What's your question?
So what is phi naught?
A finite is it's a potential. It's a process parameter. It's given to you by the process. It depends on the doping and so on. Okay. So typically, again, that's a value about 0.6 to 0.7 or 0.5, depending on the type of material. Okay. And CJ naught is also a material dependent, depending on the type of dopant and how it's doped, what is the gradient of dopant. Your CJ naught is also that value. Like, for example, this is a process dependent parameter. When I say process, when you go to a certain foundry house, like you go to TSMC, this CJ naught is different. You go to UMC, that CJ naught is different. They might be very close by for a given technology, but they're still very different. Okay. All right. So what I'll do next is, obviously a MOS is a 3-terminal. Actually, it's a 4-terminal transistor. So first of all, before I go into the MOS, why are we building this MOS transistor? Who can quickly tell me what is the purpose of building a MOS transistor? Anyone?
It's a very less size.
No, I mean, I'm asking even a more like almost a philosophical question. What is driving me? I was happy with resistor capacitors, and I have, everything, all the passive elements. What drove me to invent MOS?
So it is like having a 3-in-1.
Inverter.
What is that? An inverter? No, it's not an inverter, right? I'm trying to build an inverter. But what motivated? Like, what motivated Shockley and all those guys to create a BJT?
So like it's a combination of metal and insulator and then semiconductor.
Yeah, that I understand. That's just a combination. But why did I do that? What
Sir,
was I trying to achieve?
we can make anything from MOSFETs. A lot of things like
Like what?
all that logic gates and
How do you make the logic gates? What is the basic functionality people wanted? So, and let's talk it purely from a digital perspective. Let's not talk about analog. That's what it was created for. But let's talk it purely from a digital perspective. You're trying to create digital circuit.
calculating. Yes, sir,
What's that?
for calculation, the logic circuits were required for adder subtractor. So,
Okay, adder subtractor, good. But then what do I need to build adder subtractors?
The switching purpose.
Switching, exactly. So that's exactly what I needed for switching, because so let's keep the argument to digital only. When we do analog, I'll explain the motivation behind that again. But if you keep it to digital, so a digital function is pretty simple, right? You have a VDD, you have a ground rail, right? 0 volt. And if you want a 1 output, you want to connect this. So let's say this is the output terminal, right? If you want to convey a 1, you want to connect this to VDD. If you want to convey 0, you want to put this to ground, right? You want to short this to ground. That's basically what it is. That's your digital circuit. If you do that, you're good. And the way you do that is what? You do a switch, right? You do a switch. But you need that switch to be controlled by some control signal, right? So some control C1, let's say, and C2 voltage. So anytime I need a 1, I'll control C1 such a way that this switch is on. Anytime I want to do a 0, I'll switch this off. I'll make this control C2 such a way that this switch is on, right? So basically what I'm looking for is a switch which I can control through some control voltage, current, or whatever it is. But in this case, we are interested in controlling through a voltage. So in other words, you can say I'm looking for a voltage controlled resistor actually. So when this control voltage is high or low, whichever way you want to control it, this resistance looks like open, infinite, or it looks close to 0. So when it looks close to 0, the switch is on. When close to infinite, the switch is off. Okay, that's really what we are trying to build. Okay, a device where we have a control terminal which is controlling the resistance between two other terminals, not the same terminal, right? I don't want anything happen to this terminal. So you have a control terminal, you're trying to control the current through this terminal T1 to T2. That's essentially what you're trying to build. So for that, what you want to do is a way to control this resistance from a voltage. So in MOS, we'll talk about voltage. In BJT, obviously, you have seen how to do it through current. In MOS, we'll see how to do it through voltage. So before we talk about the switch, what we'll do is we'll talk at length about, today we'll just quickly do a review of it. Then in the next class, we'll talk more detail. We'll just look at the two terminal device, or the sandwich of the oxide between a metal. So this is your, sorry, I don't know why my, one second guys. All right, sorry. So you have an oxide layer here between a metal and some semiconductor. Okay. And this is essentially looking like a capacitor, but the difference is the other side is not a metal. So in a capacitor, you would have a metal, a oxide, or some other dielectric oxide, for example, and you have another metal here. So that's your capacitor, right? And the difference here is, instead of the other side being metal, you have a semiconductor. That's because this is what you want to control. So you want to control a channel here based on the voltage between this metal and this terminal here. Okay. So the two terminal essentially looks like a capacitor, but it is a different type of a capacitor. And if you look at the band diagram of these three different types, so you have the metal here, which, like I said, its Fermi level and conduction bands are the same because everything is conduction. You have an oxide where your electron affinity is pretty close to this thing, but your valence band is way below because nothing conducts here. And the semiconductor is what we decided, which we have talked at length before. So if you have a p-type material, just like I've shown here, the Fermi level will be close to the valence band here. Now what happens is, just from a perspective of a band diagram, I'll explain it from charge perspective next time. Let's look at it from a band diagram perspective. As I said before, now if you take these three and join them together, like you did a process where this is actually one solid material. This is like a solid sandwich. As I said before, thermodynamics tells us that the Fermi level has to be same. It has to be same for everything. So which means that this Fermi level, whatever the Fermi level was for this guy, plus this Fermi level, they have to be all same. In order for that to be same, just like in a PN diode, this band near the oxide, so this is your P type, this is your oxide, this is your metal, right? This is your P type semiconductor in this example. So obviously your Fermi level is close to the valence band. But when you put them together, because of this, what's called the work function difference, the band needs to bend, which means that, and when it bends like this, if you remember, this is a result of this side being more depleted of negative charges. So it looks like a depletion area. Okay. This just happens just by joining them, just from the fact that you've joined them and their energies, the average energy, the probability of the 50% energy, which we call the Fermi level, has to be same. Okay, like I said, I'll explain it to you a little bit more on next time when I talk about charge level, but just understand it from a band perspective. Now what you do is you apply a little bias to it. Okay, so I'm going to apply a positive bias. I won't talk about negative bias now, just positive bias for this thing. So you're applying this voltage VGB. So gate versus, we'll call this bulk. So let's call this bulk, let's call this gate. I'm just naming them so that, it kind of builds you up for the MOS terminologies as well. So when you apply the voltage, this band starts even bending further. The reason that happens is because as you're increasing this voltage, more positive charge starts building up on this metal. And if you have positive charge, it'll start building the electric field, and this has to end in a negative charge. And it so happens that it drives away the positive charge because P-type has more positive charge and leaves this immobile negative charges here, right? Sorry, I showed the wrong type of immobile charges here. It's negative here. So it leaves this, and then these electric fields, they can come here and just end here, right? So if you have the two same opposite charges, then you have electric field line here. And because it's oxide, the only thing which can exist in them is the electric field, no current flowing through them. Electric field can exist through them. So that's what happens. So this is a P-type, it just keeps driving it. You keep doing that. What happens is, if you look at this band diagram, so this is your Fermi level, right? This is your intrinsic level. Now you remember in a P-type, the Fermi level is lower than the intrinsic, right? It is lower than the intrinsic. Now look what has happened. At the very edge, if I expand this band diagram here, this is my conduction band. I'm just expanding this, by the way, this small portion of it. This is your conduction band. This is your valence band. And what has happened now is this, the Fermi level is above, the Fermi potential is above the intrinsic Fermi level. So intrinsic Fermi level was EI. Now your EF is above now, which means that this now actually looks like an N-type. Okay. So once it looks like N-type, what happens is negative free electrons starts building up. Okay. So you get what's called a charge, surface charge. And that's your channel. And this is what's called an inversion happening. The reason it's called inversion is because it inverted a P-type to a N-type. It inverted the type of material. So it inverted the type of material from P-type to N-type just from the fact of applying voltages. So your majority carrier went from being positive here to being negative. And this band diagram, it's called a full inversion when this charge density, this N E, let's say, is equal to the NP, which is directly proportional to your dopant concentration here. And by just the fact, by applying this voltage across the gate and substrate, you actually created a channel of the opposite type. So you have a lot of free electrons right now across it, and you just formed a conducting channel by applying just a gate voltage. So you had no channel. So before, no electrons actually before. So let's say you're creating an electron channel, a voltage control electron channel. So you didn't have any electron channel at all after a certain voltage, and that certain voltage is called your threshold voltage. And that's what we are going to talk in length next time as well, the threshold voltage. And it's called a threshold voltage because it's the voltage, it's a threshold volt above which you, when you go, this channel over here gets formed, or the type of the material gets inverted. So it becomes from P type to N type. So you have a lot of electron carriers right now, which is the minority carrier for P substrate, but they become the majority here. So that's why it becomes almost like an N type. Okay, is this kind of clear? So like I said, we just did a very qualitative one. We'll go a little bit more deeper into it. But is this clear? So essentially, if you just take anything away from this, you basically what you're trying to do is you're taking a P-type material and you're making it an N-type by applying an electric field. And that's your control voltage. See, I told you, right? Our main motivation was to create this switch. You want to put some VC here and be able to make a channeling current. Okay. And then I'll show you, okay, now we have created a channel. Now, how do we conduct it? What type of material do we put on the two sides? Do we put P plus or N plus or two metals, or what do we put on the both sides? And that will form your entire MOS transistor basically. Okay. So I think I'm going to stop here. I have another meeting I have to leave now. So any questions? So on the previous one. Okay, Chandan, go ahead. What's the question?
So I'm not clear about that metal side. Why the Fermi energy of metal went lower than the Fermi energy level, the real Fermi energy level,
Um,
UVG.
this one here.
Yes, sir.
Okay, well, that's just to create the equate the energy levels, because I think it'll be clear next time when you talk about it. So if you see here, the affinity here is 4.1 electron volt, whereas this is 4.15 here, and this is 0.95 here. And when we talk about work function, I think it'll be more clear. So let's leave that to the next lecture. Okay, why
Okay,
that
sir.
needs to be lower than that. It'll be harder to go into that right now. Okay. Anything else? Any other questions? All right, so I think I'll stop here. Stop the recording.